Have you ever wondered how airplanes weighing thousands of pounds can lift off the ground and soar through the sky? It all comes down to a fascinating science principle discovered by a Swiss scientist, Daniel Bernoulli, over 200 years ago. It's called Bernoulli's principle, and today we're going to break it down step by step. Hi everyone, I am Crystal Armanagi, and today I'm going to tackle about Bernoulli's principle, how do airplanes fly? So Bernoulli's principle describes the relationship between the speed of a fluid and its pressure. In simple terms, when a fluid moves faster, the pressure within it decreases. This principle applies to both liquids and gases, making it fundamental in understanding various natural and engineered systems, including the mechanics of flight. When air flows over a surface, its speed and pressure change based on the shape of the surface. A crucial application of Bernoulli's principle is in aerodynamics, particularly in how air interacts with objects moving through it. Engineers use this principle to design efficient structures that optimize airflow and control pressure distribution. The way gases and liquids behave under changing velocities and pressures has shaped advancement in transportation, medical technology, and even sports science. Understanding Bernoulli's principle opens the door to grasping how lift is generated, why certain designs improve efficiency, and how fluid dynamics impact various aspects of the world around us. It is one of the many interconnected principles that helps us explain and harness the forces that govern movement and stability. Airplane wings are designed with a special shape called an airfoil, which plays a crucial role in generating lift. This shape isn't random. It follows precise aerodynamic principles to control airflow and create the forces needed for flight. The airfoil features a curved top and a flatter bottom. As the plane moves forward, air flows under and over the wing. Due to the curvature of the top surface, air moving over the wings speeds up, reducing pressure according to Bernoulli's principle. Meanwhile, the air traveling underneath moves more slowly, maintaining higher pressure. Now that we've explored how lift is generated, let's take a step back and look at the four fundamental forces that govern flight. Every aircraft, from the smallest drone to the largest jumbo jets, relies on the precise balance of these forces to take off, cruise through the air, and land safely. So here are the four forces that govern flight: the lift, weight, thrust, and drag. First, the lift. The outward force that counteracts gravity, making flight possible. This is created by the difference in air pressure above and below the wing, thanks to Bernoulli's principle. Next is the weight. The downward force caused by gravity, pulling the aircraft toward the earth. The airplane must generate enough lift to overcome this force. Third is the thrust, the forward-moving force generated by the airplane's engines or propellers. This force propels the aircraft forward, allowing air to flow over the wings and generate lift. Lastly, the drag. The resistance force caused by air pushing against the plane as it moves forward. Engineers work to minimize drag to improve efficiency and fuel consumption. Each of these forces plays a critical role in flight, and their balance determines whether a plane is climbing, cruising, or descending. During takeoff, the aircraft must generate more lift and thrust then wait and drag to climb to the sky. Once airborne, pilots adjust the aircraft's altitude and speed by carefully managing these forces. If the thrust and lift are greater than drag and weight, the plane continues to rise. But if weight becomes greater than lift, the plane begins to descend. Bernoulli's equation explains how fluids, like air or water, behave when they move. It says that when a fluid moves faster, its pressure goes down, and when it moves slower, its pressure goes up. It's all about speed, pressure, and energy staying balanced in a moving fluid. So, let's try to solve. Imagine you are designing a water filtration system where fluid flows through different pipe sections. The water moves smoothly from a wider section of the pipe into a narrower section. At the wider section, point 1, the velocity of the water is 3 meters per second and the pressure is 120 pascal. As the water moves into the narrower section, point 2, its velocity increases to 6 meters per second because of the reduced pipe diameter. Given that the fluid is water with a density of 1000 kg cubic meter, use Bernoulli's equation to calculate the pressure at the narrower section, point 2. Assume that the pipe remains at the same height throughout, meaning gravitational effects can be ignored. First thing to do is we must understand and analyze the problem. So here is the figure. As you can see, the problem stated that we are dealing 2 points, which is the first point located in the wider pipe and the second one is in the narrow pipe. So how can we solve this? So the formula of Bernoulli stated that the pressure, kinetic, and potential is constant. And since we are dealing 2 points along the streamline, we can write the formula like this. But it is not the final formula because, as you notice in the problem, it stated there that the pipe remains the same height throughout, meaning the potential energy is no longer needed. The density times gravity times height. So we need to crush out the potential energy and write it like this. So now, let's write up the given. Using the final formula, we now substitute the given values. Then copy the P1 and the density. Then multiply the 3 meters per second in the squared, which is equals to 9 meters per second squared, and the velocity to 6 meters per second times 2, 6 is equals to 36 meters per second squared. Then multiply the 1000 kilogram cubic meter to 9 meters per second squared. That will result into 4500 pascal. Then 120,000 pascal plus 4,500 pascal is equals to 124,500 pascal. And the result in the second one is P2 plus 18,000 So the next